I hope you enjoyed that demonstration of shellcode, how to create it and understand it a little bit better. But what about debugging it if you're having a problem with your shellcode and it's deeper than just understanding the APIs that are called, for example? There are some things that you can do. So first of all, if you ever wondered how a software breakpoint works in your debugger, when you set a breakpoint, it basically just takes the byte hexcc and it replaces it with wherever you're going to set your breakpoint. And then when you continue, it puts the original byte back. And so we can do that. We can add a hexcc to the top of our shellcode, and that would allow us to single step through the shellcode. Also, if you find an exploit in the wild, you're probably going to want to put that shellcode in IDA Pro, load it as a blob as I did, hit C just like we did, and then you can either examine it statically or even step through it one instruction at a time in a debugger, just like we're talking about here. So that'll help you understand your shellcode. And if there's something wrong with the shellcode, if it's not working, there are lots of different pitfalls, many different things that could go wrong. You need a solid understanding of the bug, of the architecture, of the operating system, and so much more. There's so many details to get right. And there's things that can go wrong. For example, if your shellcode is getting corrupted as it's running, well, why would that be? Maybe there's filtered characters. I've certainly seen that before, where a particular server only accepts, let's say, characters in the ASCII range. So your shellcode really needs to be ASCII encoded. It can't include any characters outside of the ASCII range. And you can do that with Metasploit. You can actually ASCII encode your shellcode to help bypass that type of flaw, and that's very app specific. The other thing that you might want to keep in mind, and we'll see that even as we do this lab, you have to be careful that the stack pointer is pointing very near, if you're doing a stack buffer overflow, to where your input is on the stack. So if within your shellcode you are popping or pushing or doing something that would modify the stack, you could actually mess up your own shellcode as it's running. So you got to be really careful with that. The other thing you need to make sure is that, of course, all the byte alignments are very important. If you're going to send, a 1048 byte blob and you accidentally only send 1047 because you forget a null in the end or a carriage return line feed or something like that, your overwrite of a 4-byte dword, for example, could be off by one, and you're only overwriting 3 of the 4 characters. Stuff like that, you have to be really, really careful with. You have to get all the details right. And finally, there's plenty of other reasons why a shellcode might not work. There could be OS mitigations like DEP, and we're going to talk about what that is, that could be stopping it. So we'll look at all those in the coming modules. For this module, our main lab and demo is going to be a traditional Windows stack buffer overflow. And we cannot return directly to the stack as we could with some old Unix systems, because the stack pages would sometimes change in Windows even before modern protections like address-based layout randomization. That's something else we'll talk about later on. But even before that, things could change. So there was a technique called the springboard technique that allows us to bounce through a DLL that's at a fixed location. We'll search for a register at a known location that we can jump to, and I'll show you how to do that. This picture demonstrates that. So for example, if we had overwritten the return address and we realized that, let's say, the EDX register, I think is the one in our lab we'll see, actually just happens to hold a pointer to the address of our shellcode, we could find a jump EDX in some other DLL that's not protected by SLR, and that would allow us to jump through that and land it at our shellcode. And you might ask, well, why would a register just happen to hold the address of our shellcode? That seems kind of weird and random. It's actually not when you think about it, because we were just doing a copy operation, right? Copying our buffer, on the stack and all this stuff. So it's pretty likely actually that one of the registers will actually hold a pointer close to or nearby to our shellcode.